Okay, t-test is just another statistical test, just like z-test. You know, hypothesis testing. The concept and procedure for that is not going to change, but the statistical formula to calculate the probability changes. So z-test and t-test, it's really similar, and I know how to do z already, so I'm gonna look into t in this video. So this is how we did a z test. This is a formula to get the z statistic. This is for t. Okay, let's go back a little bit. Okay, this is how this is a setup for the statistical testing for z-test. So let's review. Okay, this is a population parameter, and this is the this is pre and post, and this is a post post intervention, and the mean mu we don't know, but we assume that the standard deviation didn't change. I always thought it was kind of weird, but finally this question has been addressed here in this section of the class. So it may not be the same. We may not know the standard deviation after intervention or in this population. That makes more sense to me. Okay, anyway, so that's the setup for z statistics. Okay, let's go back here. So in practice, what I just said was, in practice, we don't know the sample variance. I mean population variance, which is this. So we instead use the sample variance as an estimate of the population variance. That's the concept behind t-test, because we can't use sigma square anymore. So we're gonna have to use sample variance instead. See, this the sigma sub m standard error, this is how you get it. Actually the way we did was not like that. Okay, it's more like here. Okay, standard deviation divided by the square root of population, sample size. That's what it was. But because we don't know this, we're gonna use the sample variance instead, or sample standard deviation. It doesn't matter which, it's the same thing. Anyway, okay, where is it? Here. Okay. So recap, we use the sample variance s squared as an estimate of the population variance. So that's why okay, t-test basically sigma sub m, that's for the population standard deviation. Because we don't know standard deviation of population, we use the sample to get the estimate of the population standard deviation. So that's what it signifies, S, sample standard deviation, and it's M, right? So basically we replace the population parameter with the sample statistic. That's what I did here. It was sigma here, right? And of course SM sigma, it's just like a sigma m. Replace the sigma with the sample. I mean standard deviation or standard error In this case it's squared, so it's just like variance, sample variance. And remember how to calculate sample variance, sum of square divided by n minus 1. Why is this so important? Why it came back again? Well, it's because of this. N minus 1 is gonna be kind of important later on. It's called degree of freedom. It's denoted by df, degree of freedom. And why is this so important? Because when we are not sure the standard deviation, when we are using a sample, standard deviations, samples are not the exact representation of the population, so it varies, each time you pick the different sample. So that's why this value is going to change, each time you pick the different sample. And the degree of freedom, that's the gonna be the, so this variability is, it's a factor of, population size. If the population size is larger, then the area is going to be smaller. It's going to be really close to the population, but the sample size is small, then the estimate is going to be a little more off. So degree of freedom, because we don't know the exact standard deviation of the population, we need to take this margin of error into consideration when we do the whole statistical testing. So we can't use z-test, because z-test is based on the assumption that the standard deviation didn't change, so you can just use the same standard deviation as the original population. But t-test, we don't know, so we use a sample, and we need to take into consideration the variance, variability of the samples. Okay, so just use a regular math knowledge to replace sigma sub m with the sample standard deviation, or a variance. Then sigma m is gonna be a sm, and n is still n, but this is gonna be sigma square is gonna be s square. Just a simple replacement. And t-test is just like a z-test, but because we don't know the standard error of the population, so we have to use standard error of the mean. We have to use an estimate standard error of the mean. So that's what it means. So it's basically, it's not that difficult, just replacing sigma with s, and you just need to know what this is all about. Sm, it's not sm, it's s sub m. Okay. How do you do that? Is sm is basically this, standard deviate, sample variance divided by n, and you get the square root of that. And how do you do that? It's s square. S square is basically this, sum of square divided by n minus 1. That's what it is. And this is what I was talking about. The shape is gonna be different depending on the degree of freedom or population size. It's because because we don't know the variance. That's why each lines are formed based on different variance. And depending on the degree of freedom, or the degree of error, it forms a different shape, and notice something. If the degree of freedom is infinity, by that what it means, n minus 1 is infinity, means n is infinity, which is if n is infinity, it's actually talking about the population itself. So now you're talking about population, not the sample. So the shape is gonna be a z shape, z distribution shape. If the degree of freedom approaches infinity, then it's same as the population parameter. So it's gonna be a z. And okay, this is summary. It makes sense that d distribution would become the z distribution when our degree of freedom are infinity. That's what I was just talking about. When degree of freedom are infinity, we have our entire population. That's what I just said. So our sample variance is a perfect estimate of the population variance. If degree of freedom is infinity, then we think we're using a sample variance, but we're actually using the population variance. So we know sigma m sub m, and we are back to the z distribution. But in most cases, population is not infinity, it's kind of small, so there are variance, much more variance than margin of errors. There's a margin of error between this and the samples now, and when you take that into consideration, each time you pick a sample with a different degree of freedom, it creates a different distribution shape too. Okay.